So one more example problem here. Gasoline flows through a pipe with a radius of 1.8 centimeters at a pressure of 0.25 atm. The flow rate is 1.2 times 10 to the negative 3 meters cubed per second. At a valve which is higher than the original pipe, the effective radius is reduced to 1.3 centimeters. The pressure at the valve is 0.205 atm. How much higher is the valve? So I'm going to draw just a rough sketch. So wider, somehow in the process it becomes narrower. So the radius down here is 1.8 centimeters. The pressure down here is 0.25 atm. The flow rate, so that's our Q, 1.2 times 10 to the negative 3 meters cubed per second. So meters cubed, that's a volume, that's why this is Q. So at this valve at the higher point, the radius is now 1.3 centimeters. The pressure up here is 0.205 atm. Let me write that better. Sorry, my computer's lagging again, so it's responding slowly. So 0.2 I'm going to go ahead and call up at the top, 0.1 down at the bottom. We're wanting to know how much higher the valve is. So this is essentially going to be our Y2 when we are calling this lowest point Y1 equals 0. So to relate pressures to the moving fluid, that's always by way of Bernoulli's equation. So we can say that the pressure plus the 1/2 rho v squared plus the rho g y1, all of this stuff at 0.1 needs to equal all of this same stuff added together at 0.2. All right. So we're calling Y1 0. We're essentially looking for Y2. We have pressure 1. We have pressure 2. We know the density, or at least we can look up the density. When we look on the test notes, gasoline is listed on there, and it has a density of 680 kilograms per cubic meter. So ultimately, we need to figure out the speeds of the fluid at 0.1 and 2 in order to solve Bernoulli's equation for Y2. Oops, this is a V, not a Y. All right, so taking this stuff to the other side, that leaves me with rho g Y2. And we'll be able to solve for Y2. Just doing a little factoring out to minimize what I end up having to plug in. All right. Excuse me. Now the flow rate, it's important to recognize that we have Q and not V. I mean, the problem tells us it's the flow rate, but we can also tell simply by looking at the units. Meters cubed per second, meters cubed is a volume. And so that's why we have Q. We can relate Q to speed by cross-sectional area times speed. Excuse me. So V1 will be Q over A1. Q we know. The area, they tell us the radius at point 1 is 1.8 centimeters, so 0.18 meters. So pi r squared for this area. We need it in meters because Q is in meters cubed per second, and that will end up giving us the speed in meters per second, which is what we want. All right, so 1.1789. Again, keep quite a few digits because when we go to plug them into Bernoulli's equation, we're going to square them. So if we round much, then squaring it makes the rounding error even larger. I'm using the same equation to find speed too because I have the flow rate. I just need to use the radius in the portion 2 of the pipe. So same flow rate, different radius. Since the radius is smaller, we should expect a larger or a higher speed. .26. I went out 4, so let's go out 4 for both of them. Okay, so the continuity equation, looking at this flow rate, allows us to find the speed in this case. So now we can come back and plug into Bernoulli's equation. We have density, we have speed, we have the pressures. One note though, the terms, the 1/2 rho v squared, the rho gy, those terms are going to be in newtons per meter squared. We've been putting everything into SI units, so we will want to do that with the pressure as well. We know 1 atm is 101,300 pascals, so I do want to convert both of these pressures because every term needs to have the same units in order to add them. So this one is 25325 pascals. This one, $205. I'm getting 20766.5. And I am going to keep all those digits because I'm in an intermediate step. I'm not at an answer. So P1, we have 325 minus P2, 20766.5. The density of gasoline, again, I got that off the test notes. So 680 V1 minus V2. So those need to be squared individually, divided by our density times 9.8. All right, so let's plug these in. Okay, I'm getting, if I've plugged that in correctly, 0.49 meters. So this valve is approximately 1/2 meter higher than that original pipe. So these types of problems, we can find pressure. We could even be given a problem where we're asked to find the radius. We could have been given the height, could have found Bernoulli's equation, or used Bernoulli's equation to find V2 and take it back to find the radius at point 2. Ultimately, though, for many of our fluid flow problems, we end up needing to use both Bernoulli's equation, which is representing our conservation of energy, and the continuity equation. So the continuity equation, looking at the flow rate, allows us to relate the speeds at 2 points of the pipe because of a change in diameter. And then Bernoulli's equation allows us to come back and relate those speeds and pressures to heights.